of this was to mostly like give people an understanding of like when we talk about in class neural networks or convolutional neural networks or generative or adversarial networks or image classification, some sort of like basic, not basic, but an understanding of what we're talking about so that you can sort of know like what's possible and like what is just outside the realm of possible. So to get started, one of the first questions that people ask when they're talking about like AI or machine learning or deep learning is like, what are the differences between these things and like how are they all related? So there's this concept of general artificial intelligence, and I think that's sort of like replicating what the human brain can do. And that was sort of the initial goal of AI researchers when they started out in the 1950s, was to be able to create or exceed something that the human brain could do. And once they started going with that, they realized that they had to sort of narrow the task down a little bit more. So they started to give more sort of human input into it. So there's this term of like machine learning now. And that's sort of like a way in which, an approach in which to achieve sort of an artificial intelligent computer for a narrow task. And that still requires a bit of human input. So the one level deeper was this concept of deep learning, where instead of having some parameters being able to be modified by a human, the computer now will be able to modify a lot more parameters on its own. So to give an example of one of the first AI systems that came about was something called an expert system. And yeah, this was done, I think here at Stanford, and it was called Myosin. And the idea was that they thought that if you could just have a human input all of their knowledge into a computer, then you could get a computer to become intelligent. So their goal here was to get a bunch of experts who were doctors to be able to program this computer so that it could identify a bacteria that was in a human and recommend an output. So they spent a lot of time and money to be able to do this. But what they found is, you see they have a human expert, someone who then translates that to a knowledge engineer. They input it into this database. There's someone queries the database. They get an output, and then the user gets an output. And what's really good about these is that they're pretty simple to use, but they come at the cost that they're very, very hard to program, and not all decisions can be sort of mapped out in this way. A lot of what we do is a lot more complicated than just a decision tree. So this ended up sort of not working very well. So they kind of went back to the drawing board and said, what if instead of using a human to build these rules on their own, we could build the rules in some other way? So instead of having an expert build a system like this, they said, what if we had a bunch of data and then let the computer infer the rules on its own based on that data? And that's kind of what machine learning is, where instead of taking a bunch of rules, whereas before you had a bunch of rules and a bunch of data, and then that would produce an answer, now you had a bunch of data and answers, and that would produce the rules, which you could then produce answers with. So there's like 4 general concepts, branches of machine learning. The first, and these are all sort of based on the type of data that you're dealing with. So if you have a lot of labeled data, so that's where you have one set of data that's, for example, a bunch of images, and then you have another set of which is the labels for it, which is like what is in the image. Then you can do something called a supervised learning algorithm, where you have a pair of data, one of which is unlabeled and one of which is labeled. And the idea is to be able to transform that unlabeled data into labeled data. The next And that's useful for like image classification. So if you have a bunch of images and then transfer them into tagged images, if you want to look to see what the outline of an image. So if you have a picture of this and you want to detect the outline of all the shares of the people. The next is unsupervised learning. So that's like when you have a bunch of data, but you don't know what your goal is. Your goal might be just to visualize it or to cluster it. And there's no specific example of a goal that you're trying to achieve. So there's no label in which you're trying to get to. Basically what's going on there is this, as opposed to going to some sort of final state, you're trying to reduce the complexity of your data from some sort of very complicated state, maybe 100-dimensional, to something that's much easier to understand. The next type is something called self-supervised learning, and we'll go into more detail about these, is that that's where you have some image, some data, but you don't have human-generated labels. So what's going on there is the computer is automatically creating its labeled data. So how many people are familiar with Nightsight, which is this thing that Google's produced that allows you to take a picture and then in a very dark room and then automatically create a picture that looks like well lit. And what's going on there is they're able to produce data by just taking images that look good and then automatically sort of darken them or automatically applying a darkness filter to it, so that they are creating their own labeled image, sets of labeled images of the good images that they had and the bad images, and then figuring out a way to transform from those light images from originally dark images to light images. So this is an idea. The idea here is that I kind of put, or another example that Google's done is like automatically making images more, if they're blurry, making them sharp. So they take originally sharp images, make them blurry, and then take those blurry sharp pairs and learn some transformation between them. So this is slightly different from an example where the human has actually labeled the data. Yeah?
Can you quickly define the labeling?
Yeah, so say you have a sentence and you're trying, a human needs to, and you're looking to semantically label it. So is it a happy sentence? Is this a positive? Let's say you have a bunch of reviews on Amazon, and you're looking to see, are these 20 words that the person said, is this a good review or a bad review? So you'll have a human go through many, many thousands of reviews. Typically, you use something called a filter, which is where you label the data for you. And you'll say, read this sentence and tell me if it's a positive review, a very positive review, a very negative review, or a neutral review. And that process of taking the image that the review that you had and putting a label on it is the labeling process. Another one would be like show you a picture of a bunch of animals and say, what is the animal that is in this picture? And then you label, once you've done it, you label that image, and you now have pairs of data that are the image and the label. Okay, then the last form is reinforcement learning, where the machine creates the data on its own. So this is the example that we saw in class with those hide and go seek agents. So what happens there is that you have the agents go about in the world and produce data on their own. So here there's kind of sort of like a self-supervised thing where you're just setting up the model in which these things live, and then the agents produce data by their own feet. So here's some examples of machine learning things. So we'll cover machine learning first, and then we'll go into more detail with what deep learning is. And what really separates like machine learning from deep learning is that this is sort of well parsed and semantically labeled data. Where when you're dealing with like product reviews, you know how many stars there are, various attributes of them. Or if you're dealing with like housing prices, and you're trying to predict how much a house costs, you generally know how many square feet it has, you know how many bedrooms it has, how many bathrooms it has, and you know the thing that you're trying to get to is how much it costs. So you then take those number of parameters and you can reweight them in various ways so that And this differs from deep learning in that with deep learning, you have much more unstructured data. So unstructured data, some problems that deep learning can solve that machine learning can't are like self-driving cars and allowing them to drive because there's no structured data there, or translation when you have English text and then you're translating that into Spanish. Image captioning, so when you have an image and then producing a description of what's in it. Image classification, so given an image, say what are the objects in this image. Coloration, so you can have a black and white image and then automatically color it. Speech recognition, so having an image, having a sound file and then automatically converting that into text. Handwriting into text, so having a handwritten thing and then converting that into a text field. Yeah.
Why image classification is not considered just ML and not
Well,
just to provide learning or like not to provide learning?
yeah. So this is when you have an image like this. There's no it's not like there's no semantic labels on it. So with the house example, like you knew how many square feet it was, you knew how many bathrooms were in it, you knew its location, and then you could just sort of imagine weighting each of those parameters in some way so that you could get the target price that you're trying to achieve. You could come up with a formula. With image captioning, you just have a bunch of pixel values. Image classification, you just have a bunch of pixel values. You don't know the things that you're trying to weight. You don't know what is the equivalent of how many bedrooms or how many bathrooms are in this image. There's no parameters in which you weight, and what I'll explain in a little bit is how the computer goes about looking for parameters that it can then reweight. So that's kind of the distinction between like machine learning and like deep learning, is that the parameters that it's looking to modify are developed on their own, as opposed to needing a human to say like, oh, the important parts of this classification problem we're doing are these set of 6 things.
You still have to label data. This is a dog, this is not a dog. You just don't say the dog is head on, or like you don't describe what the dog is.
Exactly. So you let the computer come up, and I have an example actually of the cat, where what the computer actually begins to learn is it begins to look for ears, nose, eyes, and things that we typically think of as a cat, and then brings those together to achieve it. But the idea is that the human doesn't have to explicitly put in the things that it's looking for, which makes it interesting, which kind of gives another level of indirection. You do have to label the data. Yeah, absolutely. But you don't have to put in what filters what it's going to detect. So deep learning was kind of inspired by this very old neuroscience experiment where they looked at how a cat interprets images, and they saw that the cat's brain recognized lines of an object and when it moves, and that was sort of the inspiration for these neural networks, because that's why they're called neural networks. Of course, in my opinion, this probably isn't how, when we create a neural network, that probably isn't how our brain works, but that's the way they worked anyway. I don't know that we should push this analogy too far. So the way that a deep learning system works to detect an image is that when we look at an image, and this is just an example of the number 8, everything is just a number to the computer. So we take this representation of, and this is, in this specific example, it's just a black and white image. If it's a color image, you just have an red, green, and blue things that are all overlaid on top of each other. But just for the sake of argument here, it's just a black and white and gray image. So you convert all of these things into numbers, And then you sort of just lay them out in an array into a long list of numbers. And from the computer's perspective, it doesn't care what order things are in. Like the fact that that this pixel and this pixel are now sort of disjoint from each other, it doesn't matter. The convolutional neural network will handle that. So now we get into this idea of the layered network approach and what makes this deep learning so interesting. So the idea is that each layer of a convolutional neural network does some slight modification of the data. So each thing is building on the previous image. So we can see from this like cat example, if you input the image of a cat, it'll look for these various like, oh, you can't see my cursor here, can you? So if you input the image of the cat here, it looks for this side of the ear. It looks for the nose. It looks for part of the nose. It looks for another ear. And each of these layers is at the very bottom layer. It's looking for sort of edges and how they fit together. And as you go up the network, it's trying to compile those features that it's learned. And I'll explain in a second how it learns these features. But just for the sake of argument for the moment, just imagine that it somehow magically knows what these different features are. And as it goes up, and each of these layers is sort of compiling taking what from the first layer and transmitting it to the next layer, and taking this layer and transmitting it to the next layer until it's building a higher and higher representation of what's going on, of what it's seeing. So each layer is kind of distilling the information from the previous layer and passing it on to the next layer. So now what we'll do is we'll talk about how each of these layers learns the correct shape. So it's not just something that these things don't just magically appear. They need to be the computer needs to be taught them. So the learning is a process whereby you take an input, and then you feed it all the way through the network. And so we take an input here, and it slowly goes through the network here, and it outputs the word dog instead of cat. So it's wrong. And so we know that because we have labeled data, we know what we're expecting is the cat label. So what it does is it calculates something called a loss between the thing that it's expecting and the thing that it actually outputted.
It's the same as a cost function.
Yeah, it's similar. Yeah. Yeah. So it's basically saying there's some difference in what we currently predicted that is the correct value and what is the actual value. Now, what it then does is it says, I'm going to update the cat ear in the previous layer so that it more closely matches, so that when I run it through the network again, I'm going to try to gradually push each of those filters to detect ears or whatever, so that maybe I don't detect cat with 100% accuracy, but I detect it, say in the initial run through it detects cat with 0% accuracy. In the next run through, if it can detect cat with 0.001% accuracy, then it tries to do that. So it tries to update each of these filters, and this process goes on millions and millions and millions of times. So it's constantly sort of trying out different things. I might say, I'm looking for, I'm going to try just like a human ear on the cat. It's basically taking, let's just assume it's taking random guesses of things that it should be looking for, and say, I'm going to try a human ear. And then it's going to say, oh, that got a little bit closer than when I tried to look for the stem of a banana. And so it'll say, okay, I need to go in that direction. And then it'll sort of gradually climb up, looking around for features that it should detect. So it's trying to automatically detect features through this process called like gradient descent. Did you have someone have a question? Yeah.
Yeah, so if a naive assumption
feed in bad data, then it'll learn the bad data.
We trust that humans are going.
Yeah, and it's a good question because you can also have something. You can have good data and you can have bad data, but you can also have something called biased data. So maybe you're teaching it the wrong things to learn, or you're teaching it to learn things that, say, I'm teaching it to detect soft drinks, and I'm only feeding it images of Coca-Cola because I enjoy Coca-Cola more than Pepsi. And then when I show it Pepsi, it doesn't detect it because I've biased my data towards only collecting things that of type of Coca-Cola. You have a question? No? Okay. So this is kind of it. And then sort of at the highest level, here's how it works is like you take a set of things in your entire training set. So let's say you have 1 million images. You might take a batch of 10 of those and feed them through your network and get out the predicted labels. This is called your sort of Y predicted value here. You compute the loss on the batch and measure the mismatch between the Y predicted and your actual Y. You update all the weights of the network in a way that reduces the loss on that batch. So you're looking for different things. And eventually you get a network with a low loss on your training data. So now say when you run all your images through your network, you might have an accuracy of 80 or 90% after you do this millions and millions and millions of times. And this stuff isn't very hard to do. This is an example of some code to automatically detect handwritten letters, so A through Z and 0 through 9. This is on something called the MINST dataset. It's a hand recognition dataset, and you can do it in 1, 2, 3, 4, like 10 or 15 lines of code using these packages. So nobody starts from scratch in how they build these networks. Typically people use something called PyTorch, or this one's in Keras or TensorFlow, because doing this from scratch would be almost impossible. So now we'll give sort of a deeper explanation on how it works for computer vision. So for computer vision, these things use something called a convolutional neural network. And convolutional means twisted. Yeah.
Sorry, just to backtrack a bit. How do you decide how many layers these?
Yeah.
Does it matter? Like, does it make it more accurate or more efficient?
Yeah, it's a good question. Typically, people use 16 layers. So there's something called VGG16, which is like the most common way people detect images. At some point, you get diminishing return. Basically, people have tried to go 500 layers deep, but then you get something called like a vanishing gradient or something like that, where it just becomes the incremental updates become small. And the other extreme is you just have 1 layer. You just can't capture enough information. So typically people use something that's 16.
16 is random, or you just realize that's the optimal?
They just realize that's the optimal. I mean, people have also tried to apply deep learning to building. So that's referred to as the architecture. So how many layers it has, and each layer, you can imagine there's more complexity than just a layer. You can have different activation functions, so how it calculates it, or different ways the layers are connected. So you might have the first layer connected to the 5th layer, and the 3rd layer connected to the 6th layer, and 1 layer that loops around, because probably having everything directly connected straight through isn't the optimal way. So people have also tried to apply machine learning to like a meta layer around that layer to detect the optimal outcome. And that works pretty well, actually, too. But for this example, 16 layers seems to be the things. I mean, even some of the earlier things like AlexNet, I don't think was super. It was like maybe I don't remember, but it wasn't extremely deep. Yeah.
Is that scale with the size of the picture or number of dimensions, or is that?
So typically, actually, you downsample an image. So like right now, when you take a picture on your phone, it might be a 2 or 10 megapixel image, which is way too big for these networks anyway. Typically, you only need, I think, ImageNet is only like something like 32 by 32 pixels, and I have an example in later slides, but they're extremely small. It's teeny. Yeah, I don't know if that's the exact size, but it's what?
You couldn't even have a cat in 32 by 32.
Yeah, I don't know the exact size. You can actually see what's what. Maybe it's 128 by 128. I'm not exactly sure, but it's surprisingly small. So typically you downsample the image significantly, and you might even make it black and white too to reduce the complexity. Basically, a lot of the things we have are just overly complex. I'm not sure like if you're having a self-driving car or something that you would want to do that though, because you'd be losing a lot of information. But typically these things are downsampled pretty heavily. Nearest neighbor, I don't know. There's a million things you could use. You just like reduce, like just shrink it, bilinear, something like that. Yeah. Oh, okay. No, that's good too.
How do you trust the previous packages? You said that normally they don't from scratch these packages, and they trust the packages that already exist. Is there a way to pressure test these packages and say, okay, they are standard, we can trust them?
Yeah, so there's two things I want to say on this. The first is typically you actually don't. I mean, it's hard to fit everything in an hour on machine learning on AI, but typically you don't start from scratch. To answer your first question, is you don't start from scratch. You start from a pre-trained model. So each of these things might have 16 different layers, say, and what you can imagine is the bottommost layers. What they're typically detecting is just lines, like edges. It's like an edge detector. So if I'm feeding in image, if say this is trained on ImageNet, and it's ImageNet, let's just for the sake of argument, is only animals. And I have a data set of cars and trucks. The cars and trucks are still going to have the same edges and lines. It just won't get developed these. So in the 16 layers, as we were talking about earlier, the earliest layers are just sort of lines and sort of boring stuff. And as you get higher and higher up the image, higher and higher up the layers, you get more semantically relevant things. So if I'm using a neural network that has already been pre-trained on cats and dogs, what I'm going to do is I'm only going to retrain it because ImageNet has millions and millions of images, say, and my data set of trucks only has a couple thousand. I don't want to spend all my it can be computationally expensive and from a computer standpoint, and also I might have limited data. So what you do is you freeze the lower most layers on that network. So say the first 12 or 13 layers, and then you only retrain the topmost layers, and then you just have to, in response to has it been tampered with, like testing that the neural network acts correctly is a whole thing that you need to be able to verify. And there's things like F1 score, which is sort of a combination of how many false positives does it have, how many true positives does it have, how many false negatives does it have, each of those four, and then puts those all together into one number that you can calculate, because nothing is perfect. I mean, and then the other thing is like someone could try and poison the network so that it doesn't detect a stop sign or that it does something fishy, and then you have sort of a whole software problems that are associated with software anyway. Or if you download, say, an app for your computer, someone could put a backdoor in it that gives them access to a lot more stuff. But maintaining security in it is a huge problem that people are trying to solve, but I don't know if there's anything. Yeah. Yeah.
I'm maybe trying to make it simplistic, but like considering that deep learning is not a subcategory of the machine learning,
Yeah, you probably you could probably do that. I mean, one of the things that's nice about some of the other things is they're easier to reason about. So the problem with like deep learning systems, you might want to do this approach because it's really hard to reason about if you've trained a neural network to detect a cat and it has 20 million parameters, figuring out what's going on is kind of a mess. Whereas if you have like a machine learning approach and you have 50 parameters or 10 parameters, you can easily just kind of look at it and figure out what the problem is. So doing that approach or sort of finding some middle ground might be beneficial. I mean, it comes up like oftentimes what the trade-off here is explainability versus sort of accuracy. So the more typically, I'm not saying this is all 100% true, but typically like the more explainable your system is, like it's easier to understand, but it might come at the cost of accuracy. That's kind of one of the trade-offs that might happen. It doesn't always have to happen, but you get the idea at a high level.
You spoke about how the night sight in Google camera is using machine learning. Whereas
Sure.
I'm sure you know about Google Lens, right? Yeah, so that is using deep learning or machine learning?
Oh, I mentioned the Google Night Sight as a self-supervised, so where they can apply a darkness filter to. So they only have one image, say an image of a well-lit image. Then they apply a darkness filter on it because they can model what happens when you apply darkness. And what they're trying to learn is a model that when you have darkness to apply lightness, and they don't have that yet. So they have this one image. They create their own pairs of images where they have the dark image on this side, the light image on this side, and then learn that transformation between them. And Google Lens is also a deep learning thing. I mean, so the self-supervised is a deep learning thing, and also the Google Lens is also deep learning. We're trying to do image recognition on the various objects.
Yeah, I was curious about that because I do photography and the processing of an image. Like, if I had to do it myself, what I would do is click with if I wanted a good picture of a low light situation, I would click with a long exposure, short exposure, and then merge the images together to have a balance between the two. So I got from what you're saying that Google Lens is having a range of those images and then kind of superimposing them and learning from those images and then coming up with a final image.
Yeah.
So that goes more along, like it's 2 layers again.
Maybe. We can put it together. Yeah, it's fine.
Okay.
Okay, so typically how this works is that you have an image. So say there's this image of this kid on this bike. And what you do is you split it up into many, many, many smaller images. You then take each of those images, and you can see here one of the things that's interesting is that each of these images is slightly overlapping with the previous one. So there's there's more pixels here than there are here. So it's kind of taking multiple shots of the same thing. And this is where the term convolution comes from. So each of these things is kind of twisted together. It's not just through. And then what happens is you feed each of these image tiles into a small neural network, which produces maybe 5 outputs. So we have some data over here of complexity. Say this is like a 50 by 50 image, and then we're reducing it to complexity to something that's much smaller. So the end result is that we have this very complicated image, and we've reduced its complexity significantly. We then take this reduced complexity image and further reduce it down until we get the final output of the image. One thing that's really interesting about these types of things is figuring out what the convolutional neural network is learning. So what people do is they position sort of a gray box on top of the image so that they can see where the most important parts of the image are. So they can see that when they cover up, when they take a gray box and then put it over certain parts of the image, does the accuracy of the neural network go down? And so they can see when they cover up certain areas and the accuracy drops significantly, then the idea is that this is a salient part of the image. So for like a Pomeranian, if it's trying to detect this, when they put the box over the face, the accuracy drops so that they know that this is the most important part of the image. Or for the car, they're trying to look for a car wheel. When they put the gray box over that, they realize that that is the most important part of the image. Or if they're looking for an Afghan hound, they do it for this. And what's interesting about this is you can also then segment that part of the, you can use that for image segmentation as well. Yeah.
Is it important the box is gray?
No, it could be anything. It's just sort of something that's neutral, something that doesn't mess it up. Yeah.
Then do we go lower than the pixel?
Say more.
Like, is that sort of the basic unit we have? Can we go lower than a pixel? Do we still divide the pixel to like encode information within the pixel?
The pixel's the base level of information.
Is it technically possible to go lower? Like, can we create technology that sort of, because I assume that you work with larger and larger sets of data, basing, just having more and more pixels, and you go the other way around and divide the pixel to encode information within that pixel.
Well, the pixel's what's being captured by the camera. So, I mean, there is more information there. You're taking an analog thing and converting it into a discrete thing. But once it's been gone from analog to digital, you can't back it back out. You can take a digital image and like there's something called a subpixel when you're displaying information. So when you have a computer screen and you want it to look like the edge of a font is more closely rounded, you can mess around with which colors light up so that it gives it a more natural look. And I think Apple does that. But I don't think you can divide lower than a pixel when detecting it.
So the idea is simply that if you vastly expand the data, then any given pixel is relatively small.
Oh, I see. So I see what you're saying. So if we did it on this size data set and then we used a much larger image, would it be able to segment out the larger image? I don't know.
I guess we treat pixel as this lowest unit,
Uh-huh.
and simply in order to make it sort of less variable based on any given pixel, you expand the data set so that any given pixel is relatively smaller than the entire system. The more you expand it, while keeping the pixel size the same.
Yeah, I'm not entirely sure, but we can talk about it later. Just for the sake of this, just imagine each pixel is the lowest thing that we can go at. Okay, so this was something called a convolutional neural network. And what's interesting about this is it works for images because images are all fixed sized. So you have one giant block of images. They're typically all the same size, at least or you can resize them to some fixed size. You feed them through the network and you get a label out. Now, let's say you're dealing with text. So you have something of variable length size. So no longer you might have a sentence that is 10 words long, but you also might have a sentence that's 50 words long. So how do you go about dealing with that? So someone has come up with this idea of a recurrent neural network, where that instead of having an input of fixed size, you can have an input of variable length size. And some of the things, let me just show you this. This is sort of, right here is a convolutional neural network where everything is just going through in one pass. But here you can see each of these nodes is connected to other nodes so that things can keep looping around until you've reached some final state. And so before what we had is we had images that were directly converted into, that picture of the 8 with the zeros and ones. Here what you do is you assign each word sort of a number, let's say. So let's say if you just took a dictionary and the first word in it was apple, you'd assign that the number 1, and then just assume the next word was banana, you'd assign that the number 2, and you just keep making it larger and larger. You just convert each word into some integer. That's not how it's represented, but it's put into a vector, but it doesn't matter. So some of the things that you can do with recurrent neural networks are you can do translation, so like Google Translate. You can do summarization. So on one side, you can have a very, very long document of maybe 100 or 200 words, and you can convert that into something that's of like size 10 words. You can do sentiment analysis. So you can take a document and say, is this a positive review or a negative review? And you can do like question answering even. You can say like, here is, what city did the Tesla move to? What city did Tesla move to in 1880? And it can answer Chicago. So in the input to that is the question, and then the output to that is the answer. So you can do very, very complicated things actually, just using this recurrent neural network model. Does anyone have any questions on that? No? Yes? It means that go over here actually, that way people online can see. It means that it's instead of going from this node. So this is the image right here is the lowest level, and then this is the tag, the label for it. What's going on in a recurrent neural network is instead of it outputting a tag immediately, it's feeding its previous state. It's feeding the output back into the network as an input. So it's taking, it's relearning the state from its previous. It's just imagine just one instead of many small nodes. It has one giant node that is sort of learning the state of all the inputs it's seen so far and updating that. So it's recurrently taking what it previously had and inputting it back into the system. Okay, so one of the reasons that people use these frameworks like Keras and TensorFlow that I talked about before is so that they can easily use like a CPU or a GPU. And these things are necessary because what I talked about before with like needing to do this step millions of times, if you were to do that on a CPU, would take days or weeks, whereas on a GPU it might take only an hour or two. And so this slide sort of tells you that a CPU might have 4, 8, or 16 cores, but a GPU might have 3,000 or 4,000 or probably even a lot more now. And it's probably more expensive, but you get a lot more power out of it. This comes at the cost of you can't do as complicated of things, but the things that you're trying to do are these sort of matrix multiplications that are actually pretty simple to do and can be done very quickly on this. And this is sort of one of the things that's enabling people to do this research now. And then this other slide down here shows how many gigaflops you get per dollar on a CPU, which is blue, or on a GPU, which is orange. And you can see, just from a cost perspective, it becomes, when you have such a high factor, it becomes much easier to do. So now we'll talk a little bit about data. So I think there's this thing, this is from the book Deep Learning. So if anyone wants more information about this, a lot of these slides are from this book called Deep Learning Using Keras, which is that thing that I referenced earlier. And they say in the book, if deep learning is the steam, then data is the coal. So that's sort of the thing that's fueling everything to work. ImageNet is one of the first ones to large data sets that was used by machine learning researchers. And they compiled many thousands of millions of images and using Mechanical Turk to have people label them. And these are images in it. You can see they're actually pretty small. Like, they're not very high resolution. And what was interesting about this is that it sparked a whole competition about who could do best, who could do the best job on classifying images. And here is sort of the initial thing, the initial results. And you can see this was the first convolutional neural network here. And there was a huge jump in accuracy. And from there, it just sparked. What's interesting about this is that this data set sparked a huge competition. Okay, so now we're going to talk a little bit more about data and the importance of trying to validate your network. So what do you think would happen if you trained on all of your data? So say you had 10 images of cats and you trained your deep learning model on those 10 images, and then you got 100% accuracy on that. Well, what would happen is that when you fed in the 11th image, it might not do so well because it does something called overfitting, where you've learned too much about the images that you've put in, and you'd have no way of testing if how it will work on future images. So typically what people do is they don't use all of their data for training. So they'll reserve part of their data for something called a validation set. So you might use 70% of your data to train your network with, and then you might keep 20% of your network to test your network with, to validate your network, so that you know you're getting closer and closer to some optimal things so that you're not overfitting. And then you might also keep a little bit of your data, say 10%, as a final test set to say, and when you're finally testing it, to say this is how well the network does. And so this is one way in which people try and prevent overfitting, is by not using all of their data. Because otherwise what you can have is your model learn everything about all the data, and you could just sort of cache it all and then get 100% accuracy. But that's not super helpful, because then it won't do very well when it's out in the real world, not on data that it hasn't seen before. So believe it or not, now we'll talk about sort of other things about deep learning and stuff, and that's how it can be used to generate images. So these images here of the person and the birds and the bedrooms are all done by generated automatically by a computer. And what's cool about this is that they're done using something called a generative adversarial network. And this is like a really interesting concept. And the way it works is that imagine you had a painter who's trying to paint a fake Mona Lisa, and then you had a dealer who's saying this is good or bad, this is a good or a bad fake. And so the person who's trying to fake the artwork is constantly learning how to create a better fake, and the person the art dealer is constantly learning, becoming more and better at comparing. So in this example here, you have a real data, which is the real Mona Lisa. You have someone who's generating these fake Mona Lisas, and then you have a detective who's looks at the real one and looks at the fake one generated by this forger, and then gives the forger feedback on how to create a more and more accurate thing. So what the forger is then doing is learning how to create images that look very similar to the real image, but has some amount of leeway in what they create. So they're not trying to create it exactly, but they create things within scope of it. Yeah.
Sorry, would that be giving you information about what should be reached, or just yes or no, whether it's a good thing?
You could just do yes or no. It would just take longer for the generator to learn what an accurate representation is. The good thing about giving feedback is that it learns more quickly. And of course, yeah, feedback in this term is through gradient descent or some optimization means. So with this, you can now start, do you have something? No? You can now start producing images automatically that look almost identical to a real image, which is kind of interesting. Another thing is creating attacks on neural networks. So, yeah.
So the adversarial networks is actually two networks
Yeah.
set against each other.
Yes.
Is the discriminator and one is the generator.
Yes. Yeah. So one is generating images. One, like here, it's let's just say this thing that says latent random variable is its creative genius. And so it's sampling its creativity for something and producing an image that it produces, and it samples it, and then it also has real world data, so the discriminator knows how to compare it against something, so it can say, like, is this close or not? And the idea is that you're sort of optimizing this latent space, how it samples this latent space, and the process of generating after it, so that in the future, when the discriminator is not there to optimize it, it can still produce images that are accurate.
With text as well, right?
Yeah, you can.
Literary text.
Yeah, you just need to have a way of calculating the difference between correct and wrong. So it's a really interesting idea. Kind of related to that is to show that neural networks aren't perfect. So you can take an image of this panda here and then add some random noise to it and automatically get it to say that it's a gibbon. By carefully this isn't random noise, actually, it's carefully chosen weights to push pixels up and down so that you fool the network into thinking that it's something that it's not. And so you can imagine someone has also done this for a stop sign, where they took a stop sign and very accurately calculated how to manipulate it so that it appears to the neural network as something that it actually isn't, as a way of fooling it. So this is what happens when your test set and your validation set, or you have someone who's trying to muck with your system, happens. So these things aren't perfect, and I think there's a lot of interesting legal implications when you have this type of thing as well. Were there any questions? That is the end of I think we're hitting an hour exactly, so if there's any questions, you can ask me. Yeah?
This is a question returning back to bias, bias, whole system. And I understand you can fix bias by feeding in that data. Right? Having your patient working in software, you like feed it all white faces and say that's a face, and you put like color in fabric. But how else can that bias occur in the process? Like, I know you give the example of like the FC, but can you talk through that a little bit more?
Yeah, totally. There's other biases where Yeah, yeah.